All right, so this is the first part of chapter 20, which is electrochemistry. This whole first video is officially review from chapter 4. So in chapter 4 in Gen Chem 1, at that point in your chemistry lives, you would have known how to balance equations. You would have been learning about all the different categories of chemical reactions. So like combination, decomposition, combustion, single displacement, which we called displacement, and double replacement, which we called metathesis, acid base, all that kind of stuff. One of those categories is reduction oxidation. So that one category of reaction, you learned some things about it, like what the words meant for reduction and oxidation. You also learned what an oxidation number was, and things like that. But that was one tiny part of chapter 4. Chapter 4 was huge. You also learned about molarity and the dilution equation, and there's a lot going on. So this video is pretty much going to review what you were supposed to learn about electrochemistry back in chapter 4. And I don't want to make any assumptions that you either learned it up front or that you still remember it. So just a heads up, when you look in your textbook, not all of this stuff, like it's mentioned in chapter 20, but the details are back in chapter 4. So I just wanted to give you that heads up. Also a heads up, chapter 20, electrochemistry. Electrochemistry is a very important branch of chemistry. Electrochemists are among the highest paid chemists. They're the ones that are working on like batteries and fuel cells and whatever. So it's very important, and we need electrochemists. But I'm biased because I think electrochemists are weirdos. So electrochemistry is not my favorite topic. That, again, it's very important, and it's something it's actually within the branch of chemistry that I love, which is analytical chemistry. It's the people that figure out like how much of something was in there. So like if they're doing a drug test on someone and they want to know how much cocaine they've had, that's the analytical chemist. I don't know why that was the first thing I thought of, but electrochemistry is within that branch. I just don't love, I think it's more my experiences with people that are electrochemists, but I say that, and our new professor, Dr. Lyon, is an electrochemist, and I like him, so I don't know, whatever. Electrochemistry isn't my favorite. That being said, it's super important. We're still going to talk about it. But if I ever am like grumbly, it's not to you guys. It's to electrochemistry as in general. There are several things, and I'm sure I'll tell you about them, that I think are dumb and that they could have been done better. But again, I have no power in this world of chemistry, so I just have to tell you the way things are. Okay, after my little rant, let's actually start chapter 20. And if you like electrochemistry, good for you. I'm not going to be angry at you. We've had people that left St. Charles Community College, went on to universities, and are now working as electrochemists. So my goal is not to dissuade you from being an electrochemist. I'm just telling you that I have a bias against it, and to know that, and it's not aimed at you. It's my own personal problem. All right, so objectives, blah, blah, blah. So a redox reaction. So redox, that term comes from reduction, oxidation, and just smushing the first couple letters together, because reduction, oxidation takes a long time to say, where redox is not taking as long to say. So a redox reaction is a reaction where electrons are being transferred from one substance to another. So one element is gaining electrons and a different element is losing electrons. And both of those things have to be happening. We have to have something gain and something lose, because the electron has to be transferred from one substance to another. So if something loses an electron, it has to go somewhere. So there has to be something that's gaining the electron. Or if something gains an electron, it had to come from somewhere. So it had to be something that's losing that electron. So reduction and oxidation, we need to know their definitions. So oxidation is the substance, is when something is losing an electron. And I put a positive sign after that, because when something loses an electron, its charge, or its oxidation number, which is how we're going to define charge in this chapter, becomes more positive. So more positive. That could be from a 0 charge to a +1. Or it could be from a -2 to a -1. That's still a positive change. I know both numbers are negative, but we're looking at how the charge moves. So the charge becomes more positive. So reduction is the name for the process for the thing that is gaining electrons. When something gains electrons, its charge is going to become more negative. So it might go from 0 to -1. That would be evidence of reduction. It could go from -2 to -3. also evidence of a reduction. It could go from +4 to +2. That's also evidence of a reduction because although both numbers are positive, 4 decreases when it becomes 2. So reduction is when the charge becomes more negative, not necessarily that the number itself is negative. You're going to need to know these words, and one of the basic things, the first things you're going to have to do in every problem in this chapter is going to be able to look at a balanced equation and determine what is oxidized and what is reduced. So there are all kinds of mnemonic device sorts of things, and the one that I like the most is Leo the lion. Oops. Goes grr, and I did not give myself enough space for this. Leo losing electrons. So Leo losing electrons is oxidation. And grr, gaining electrons is reduction. There's also oil rig. There's a whole bunch of different things. I just like that one. I don't know why I don't have it on here, but I have a picture of a lion and it just says Leo goes grr. So anyway, know these definitions. So know the words, but also be able to identify them. And that's part of what we're going to practice here. So oxidation and reduction always have to go together. In one reaction, there has to be something that's oxidized and something that's reduced. If you think there's 2 reductions, or if you think there's 2 oxidations, or you think there's only one and not the other, you're wrong. So you need to go back and check it out. Okay, so in order to determine if something is being oxidized or reduced, we have to look at its charge to tell if it's becoming more positive or more negative. So when we're looking at electrochemistry, they don't call it charge. They call it oxidation numbers. And that's because charges is very specifically for ions. Now, what we're going to be looking at is sometimes we have molecules or polyatomic ions that inside of them have covalent bonds. And so those covalently bonded things do not have a charge like an ion because they're not ions. So oxidation number is just kind of a more general term. I'm really bad at calling them oxidation numbers. I'm just warning you right now, I'm going to call them charges, not on purpose, and I'm going to try to correct myself. But to me, I mean, I get that there's a technical difference in their definition. You know, charge is for an ion, oxidation number is for an ion or a covalently bonded compound. To me, they're all the same idea. So, anyway, so here's the rules. The rules for assigning oxidation numbers. Number 1, if it's a pure element, so it is just in its pure elemental form, so like a chunk of copper metal, or oxygen gas, O2, or hydrogen gas, H2, or sulfur, which is S8, or phosphorus, which is P4, just pure element by itself. Its oxidation number / charge is 0 because it's like in its original form. It's got the same number of protons as it does electrons. That's the way that the atom was created. So pure elements have an oxidation number of 0. So just a reminder, sometimes pure elements come in groups of 2 or whatever, like those 7 diatomic elements. That's their pure elemental form, so they still have an oxidation number of 0. A monatomic ion, that is something like this. So it's mono, 1, atomic, atom. So one atom that's an ion. So one atom that has a charge. Its charge is the same thing as the oxidation number. So like in this case, calcium 2+, or +2 if you want to say it that way, is the oxidation number. Okay. I'm going to come back and talk about 3, 4, and 5 in a second. Number 6 says the sum of the oxidation numbers equals the overall charge, 0 in a compound. So this is coming back to something that you actually already know. If I have the compound MgCl2 as a compound, there's no charge written up here, right? And if there was, it would be 0, because back in Gen Chem 1, when you learned about putting ions together, so that way the charges cancel, when you put ions together to make the charges cancel, to make a compound, all the charges canceled, which means their overall charge is 0. So I'm going to do another example. I'm going to do CuNO3, 2. So you had to utilize this back in Gen Chem 1. So do you remember the transition metals, the D block elements, group 3 through 12 on the periodic table? Those elements do not all have the same charge, right? They're transition metals because they can have multiple charges. So if we're looking at a compound, copper is one of those elements. We don't know what copper's charge is. There we go. All the time, because it has a couple different options of what it could be. So when we were naming these compounds, we had to do something where we wrote their name, like the name of the element, copper, but then in parentheses we had to write its charge in Roman numerals, and then we wrote the negative thing, okay? But that charge, again, we had to figure that out. So in this case, what we did was there's a copper, and there are 2 nitrates in this compound. So nitrate, we would have to remember, is a -1 charge. So, really? Pen, you and I are not friends. All right. Those add together to equal -2. That's what we've got. Okay, so in order for this to be a compound, then copper had to be able to cancel that out. So I would know copper was a +2 or a 2+. So over here in Roman numerals, I would write the 2. Okay, that was using number 6. Okay, just saying the overall charge is 0 for a compound. So you can use the idea of that to solve for anything that's unknown. Now, what we didn't do in Gen Chem 1 was something like nitrate. If I'm just looking at nitrate and I want to know the charge or the oxidation number on oxygen, the nitrogen and the 3 oxygens add together to equal not 0, but -1. Okay, so we can take the total of the 1 nitrogen and the 3 oxygens and they equal -1. So when we're looking at a compound, the charges add together to equal 0. If we're looking at an ion, like a polyatomic ion, they add together to equal whatever is shown up there. Okay. So numbers 3, 4, and 5. Back in Gen Chem 1 again, we assigned charges to different groups, different columns on the periodic table. Group 1 was a +1. Group 2 was a +2. Group 13, which starts with boron, and goes down from there, was a +3. Group 14 you should have skipped and not learned anything about. Group 15, which starts with nitrogen, was a 3-. Group 16, which starts with oxygen, was a 2-. Group 17, which starts with fluorine, was a 1-. And group 18 had a 0 charge. So it turns out that group 1 is a +1. Absolutely 100% yes. When it's an ion, everything in group 1 is a +1. Group 2 is a +2. Absolutely 100%. When any of those atoms are ions, they are 2+. Group 13 is a +3. Yep, 100% again. Everything in group 13, when it's an ion, is a 3+. Group 14, well, we didn't put a charge on that because they're treated like the transition metals. They can change. Group 15 being a 3-, well, you know, it can be. It can also be other things. Group 16 being a 2-. Yeah, again, that's one of the choices, but there are other choices. Group 17 being a -1. Again, sure, but they can also be other things. So it turns out that group 15, 16, and 17, we have to treat them like transition metals, meaning we don't always know their oxidation number. We gave you charges in Gen Chem 1 that are the most common charges and asked you to memorize those, the 3-, 2-, 1-. Not because we were trying to be tricksy, but because we needed to have a starting point, and that is their most common charge, but that doesn't mean that's the only option they have. So because of that, those 3 groups, there are only 3 elements that are nonmetals, which those all encompass the nonmetals, that we can guarantee we know their oxidation number: hydrogen, oxygen, and fluorine. Okay, so hydrogen, and actually I'm gonna, yeah, sure. I want to add myself a new slide in there, and we're gonna go to that. Nope, not like that. We're gonna, I'm gonna write some stuff down. I missed the whiteboard. Okay, so for rules number 3, 4, and 5. So hydrogen. Hydrogen is an element. It can be a pure element, which is how hydrogen exists as a pure element, as H2. It's a 0 oxidation number at that point. Hydrogen can be a +1 charge, which is what we dealt with all the acid stuff, right? It was H+. That is, so hydrogen is a +1 when it's bonded to nonmetals. Nonmetals, the elements on the right-hand side of the periodic table. Things like fluorine, chlorine, bromine, and iodine. Like when it was HCl, HBr, HI, it was an H+. Okay, but hydrogen also has one other option. It can be a -1. That is true when it's bonded to metals. These are called hydrides. So something like this. So one clue is that hydrogen's at the end. We always put positive charges first and negative charges second. But this is why on the periodic table that I gave you guys, hydrogen is in 2 locations. It's in group 1 and it's in group 17. This is actually why. Okay, so those are the options for hydrogen. So we can look at a hydrogen in any compound and decide, or in any scenario, and decide what its charge is based on these rules. Okay, so that's why it's one we can count on. The other one, or there's 3, but oxygen. So oxygen as a pure element, which I guess I should have written there, it can be 0. Most of the rest of the time, oxygen is a 2 minus. The only exception that we're going to worry about is the lovely peroxide polyatomic ion. It's one of the polyatomic ions from Gen Chem 1. If we have 2 oxygens and together they're a -2, that in the peroxide ion, each oxygen is a -1. So the only time that we're going to see this, I'm going to be really clear about when something's a peroxide. Like I'll probably put its name there and it's going to have the name peroxide. So oxygen is a 0 charge, 0 oxidation number when it's a pure element. Pretty much 99% of the time otherwise, it's a -2. The only exception to that is if it's a peroxide and then it's a -1. And again, I'm going to be super clear about when something's a peroxide. Our last element that we can rely on is fluorine. So fluorine as a pure element is F2. So then it's a 0. The rest of the time, fluorine's a -1. That's it. There's no other options. Okay, so fluorine's the most straightforward one. It's just not one we see all the time. So those 3 elements, we can trust those. All other nonmetals, so groups 14 through 18, I guess, we don't know, which means we have to solve for them, like we did the transition metals. Okay, my handwriting's not great. So this is what rules 3, 4, and 5 were trying to tell us. So what we're going to do now is let's practice. So we've got 5 examples here. We're supposed to find the oxidation number, which again means charge, for sulfur in each of those scenarios. So I'm just underlining it. Since I was asking for the same element in every time, I gave you that in the question. If it was 5 different compounds where I wanted to know the oxidation number of 5 different elements, I would have done this and I would have underlined the one that I was looking for, and that's what the instructions would have said. I don't know if you guys can hear this, but my dogs are running laps around the house. So if you can hear claws on hardwood floor, sorry. Okay, so we're solving for sulfur. So the first thing I do is I look at the thing that I'm solving for. And sulfur is one of the elements. It's one of the nonmetals. It's in group 16, so I don't know what its charge is, so I'm going to have to solve for it every time. And let's decide what is the overall charge. Like, what's the charges, the oxidation numbers of everything added together? Well, this is a compound. And I know it's a compound because there's nothing right here. So what that tells me is I make myself a little algebra equation. Well, there are 2 hydrogens, and there's 1 sulfur in this. And their charges are going to add together to equal 0. We're trying to solve for sulfur. So we need to substitute in a charge for hydrogen. Well, if we look at the previous slide, hydrogen is one of the elements we can count on. It has 3 options. It's a 0, it's a +1, or it's a -1. Well, in this case, hydrogen is not a pure element. I know it's H2, but it's when it's H2 gas by itself is when it's 0. That is not the case here. It's H2 plus an S, so it's something. So it's either going to be +1 or -1. So if we look at our criteria, sulfur is a nonmetal. So that means hydrogen's a +1. So 2 hydrogens, I'm just going to write 2 there, because it's 2 times +1. 2 plus sulfur equals 0. Treat this like an algebra equation. Let's solve for S. So I subtract 2 from both sides. I get -2, which I'm going to rewrite as 2 minus. So in this case, sulfur is going to be 2 minus. Okay, I'm going to change color just to keep track of my work here. Okay, so S8. When you look at that, you might not immediately recognize it as anything, but if we can look at it as so S8, what is its overall charge? Well, we're looking up here, and I don't see anything, so that tells me a 0. So if I use algebra, I'm going to divide both sides by 8. I'm going to get S equals 0. This is actually what sulfur looks like as its pure element. Again, I don't expect that you know that, but we could figure it out. Green. No, actually, we're going to come back and do the third one last. We're going to do this buddy next. So Na2SO3. When I'm looking at this as a compound, the overall charge of all the pieces added together is going to be 0. So I'm going to say 2 sodiums, 1 sulfur, and 3, I'm going to write OXY instead of oxygens because it doesn't mean 30 or 3 times 0. But all those added together to equal 0. So we're supposed to be solving for sulfur. That means I've got to plug in a charge for sodium and a charge for oxygen so that way I can solve for sulfur. So sodium, we look at it on the periodic table. It's in group 1. That is group 1, group 2, and group 13. We can trust what we learned about them in Gen Chem 1, which sodium in group 1 has a +2 charge. So 2 sodiums is going to be a +2. Sulfur, I don't know. So 3 times oxygen. So oxygen was on the previous slide where it had 3 scenarios. It's either a pure element, it's a -2, or in a peroxide polyatomic ion, it's a -1. Well, it's not a peroxide and it's not a pure element, so it's -2. So 3 oxygens, I'm going to write -6, -6 there. So when I do algebra, 2 plus -6 is going to give me -4. So sulfur minus 4 equals 0. Sulfur equals 4, but I'm going to rewrite that to look like a charge, so 4 plus. Purple. Now we're going to do this one. So 1 sulfur and 4 oxygens, what do they add together to equal? Do you think it's 0? Because it's not, and I know it's not because it says -2 right there. So instead, 1 sulfur and 4 oxygens add together to equal -2. So we're solving for sulfur, okay? So I need to plug in a charge for oxygen. So we got to think back to the previous slide. It's not a pure element. It's not a peroxide. So oxygen's a -2. So I'm going to write S minus 8 equals -2. So 4 times -2 is where the -8 comes from. I add 8 to both sides. Sorry, that's a -2. And I get a 6. Okay, well, to show it as a charge, I'm going to write a plus sign after it. I didn't give myself a whole lot of space. But SCl2. SCl2, the 1 sulfur and the 2 chlorines, I'm going to say they're adding together to equal 0. We're supposed to be solving for sulfur because that's what the question asks for. Okay. So the 2 chlorines, we've got to plug in a charge for chlorine. If we look at chlorine in the periodic table, it's in group 17. The issue is it's in group 17, which means group 15, 16, and 17, I told you not to trust what we said in Gen Chem 1, other than the elements that were on the previous slide. Chlorine's not one of those. But we're solving for sulfur, so I have to plug something in for chlorine. So if you're in the situation where you have to put in a charge for the element, you just have to fall back on what we learned about in Gen Chem 1. So group 17 and Gen Chem 1, we called it a -1. We're just going to have to assume chlorine's a -1 because otherwise I can't solve this problem. So sulfur minus 2 equals 0. So sulfur equals 2. I'm going to add a plus sign there to show that it's a charge. So that's if you have to fall back on what you learned in Gen Chem 1, you know, sometimes you have to like that. I'm going to try not to put you in that situation very often, but it may happen. So this is how we can solve for oxidation numbers. So my suggestion, oh, look, good job. We got the right answers. Here's another set of examples. P2O5, where the bolded and underlined thing, you're supposed to be solving for phosphorus. NaH, the bolded underlined thing, you're supposed to be solving for hydrogen. For dichromate, you're solving for chromium. And by the way, in this case, and in this case, you're solving for one of those atoms. Like, what's the charge on 1 phosphorus? What's the charge on 1 chromium? For tin, and for BaO2, where I'm telling you this is a peroxide. So I would like you to try, like, hit pause and try at least 3 of these right now. I would suggest trying this one, and this one, honestly. But you can do any of them. And then what I'm going to do is I'm going to show the answers here. But if you're going to practice, why don't you hit pause on the video and try it right now to see how you did. Okay, so hopefully you practiced. Here's the answers. So the peroxide, it was a -1. But on all the other ones you were, and with this NaH, it was a -1 because hydrogen was a hydride in that case. Sodium's a metal. Okay, so if you do these and you did not get the correct answer and you've got questions, please let me know and I'll help walk you through that. But for right now, I just wanted to use those as practices. Okay, so our review. It's kind of some vocab stuff. We already talked about what oxidation was and what reduction was. But in electrochemistry, there's a lot of words that mean the same thing. So I'm going to add to that, which actually means I should have thought of this for sure. And I'm going to give myself New slide. Okay, so, and then I'm going to have to do the thing where it's showing me, yep. Okay, so these are words that mean the same thing. So when something is, or undergoes oxidation, that means that whatever it was is oxidized. Okay, just words that mean the same thing. Another set of words that mean the same thing is something that undergoes oxidation or is oxidized is called the reducing agent. I don't know why, because electrochemists are weird. That's why. Okay, I want to change my color. There we go. So if something undergoes reduction, we could say that it is reduced, and it's also called the oxidizing agent. So as we go through this chapter, I'm going to be adding more words below this that mean the same thing, because that's what we did, was electrochemists made a whole bunch of things, a whole bunch of words that meant the same thing. Grumble, grumble. Okay, so let's practice looking at an equation, identifying what is being oxidized and what is being reduced, which the way the question is actually asking that is what is the reducing agent and what is the oxidizing agent. But for me, first I find out what is oxidized and what is reduced, and then I think about what the words mean. So in order to figure out what is oxidized and what is reduced, we first have to figure out the oxidation numbers for everything. So I'm going to do, so like the things we just practiced, we're going to do that, but for everything. I'm going to do the easy ones first. So the easy ones are either the ones that are pure elements, so I don't have to do any math, or the ones where their oxidation number is like already showing. Okay, so hydrogen is a pure element, 0. Aluminum is a solid, is a pure element, so 0. Okay, the other two things we're going to have to solve for what they are. So HBr. Well, we know that hydrogen and bromine are going to add together to equal 0. Now, hydrogen is one of the elements that we can count on, so we got to think back to the rules. So hydrogen is either a pure element as H2, that's not in this case. It's either a +1 when it's bonded to a nonmetal or a -1 when it's bonded to a metal. Bromine is a nonmetal, so hydrogen's a +1. I'm just going to write plus right there, which means I can substitute for it here. So I do my algebra, and bromine is minus. Okay. Aluminum bromide. Okay, so aluminum, Al. I look on the periodic table, it's in group 13, which is one of the groups that we can trust. So it is a 3+. I also know that 1 aluminum and 3 bromines add together to equal 0. Okay, so if aluminum is a 3, when I solve for bromine, I get a -1. Okay, so what we're doing is we're looking for the element that is becoming more positive and the element that is becoming more negative. Now, in this situation, we have 3 elements, aluminum, hydrogen, and bromine. One is becoming more positive, one is becoming more negative, and one isn't changing. So the one that's not changing is not oxidized, it's not reduced, it's just hanging out. Okay, so 2 elements that do change are aluminum and hydrogen. Bromine does not. So as far as we're concerned, we don't really care about bromine. Okay, so aluminum goes from a 0 to a +3. So we got to think, does that become more positive or does that become more negative? Well, 0, it moves up to become more positive to a +3. So it's becoming more positive. So we have to think what that means. Well, if something's becoming more positive, it is being oxidized. Okay, so aluminum solid is being oxidized. So what kind of agent is it? Well, remember, it's the weird thing. It's the opposite. So this is the reducing agent. So hydrogen goes from +1 to 0, which is a negative change. It's going down. So it's being reduced. So as an agent, it is an oxidizing agent. Okay, let's do one more. So again, this is one that I would have told you guys, hey, stop, why don't you practice this? And then we're going to go through it. So why don't you take a second and pause. I want you to find the oxidation numbers of everything and then decide what is being oxidized, what is being reduced, which one is the reducing agent, which one is the oxidizing agent. Okay, so hopefully you practiced. I'm going to do the oxidation numbers first. I'm going to go with the easy ones. So magnesium is a 0. Cobalt is a 0 over there. I'm going to be lazy about something. Do you see how SO4 looks exactly the same on both sides? And if you recognize it, that it's a polyatomic ion, then I'm going to just treat it like a polyatomic ion and not solve for sulfur or oxygen, because I can tell that it didn't change. If you solved for sulfur and oxygen, that's great. It was just more work than you had to do. So for this one, I have cobalt and I have sulfate, and I know they add together to equal 0. So if you remember your polyatomic ions, sulfate is a -2. Okay, so that means cobalt's going to be a 2+. And then over here, got to solve for magnesium. Well, actually, to make it even easier, if you look at magnesium on the periodic table, it's in group 2, which is one of the groups we can trust. So it's a 2+, and then sulfate itself is a -2 and didn't change, so I'm not worried about it. We could also look at it as magnesium plus sulfate equals 0. So if we didn't know magnesium, we could solve for it here. So looking at oxidation numbers, magnesium and cobalt were the two that changed. So magnesium went from a 0 to a 2+. So it became more positive. So it was oxidized, making it the reducing agent. Cobalt went from 2+ down to 0, so it became more negative. So it was reduced. So it's the oxidizing agent. Okay. So that's going to be kind of first steps in every problem that we do for the rest of the chapter, is going to be to find out what's oxidized and find out what is reduced. Okay, so hopefully that helped. And the last reminder thing that we have is about net ionic equations, because it's actually a lot easier to look at redox reactions if they're in net ionic form. Net ionic form is when we cancel out the spectator ions. So I'm just going to go back to the first equation we practiced if it's reduced or oxidized. And we're going to practice, we're going to remind ourselves how to do a net ionic equation. So to do a net ionic equation, you have to identify the strong electrolytes. The strong electrolytes are the 7 strong acids, which at this point in your life in Gen Chem 2, I hope you know the 7 strong acids. Do you see any of the 7 strong acids here? Because I do. HBr is a strong acid, so I'm going to write Se for strong electrolyte. Okay, so strong acids are strong electrolytes. Weak acids are not, so we would ignore the weak acids. Like, they would not be strong electrolytes. The other type of strong electrolytes are the soluble ionic compounds. I told you in chapter 17 you did not have to memorize the solubility rule. So how you're going to recognize the soluble ionic compounds. It is aqueous, and it is not an acid. Because at this point, we've learned to recognize acids. I'm hoping you've learned to recognize acids. Acids start with H's. Okay, so if it's aqueous, so we have 2 things that are aqueous. One of them is an acid, and it was a strong acid, so it's a strong electrolyte. The other one is not an acid, but it's aqueous, so I'm going to call it a soluble ionic compound, so it's a strong electrolyte. Aluminum solid and H2 gas are neither one of those. If something is a solid, a liquid, a gas, it is not a strong electrolyte. If something is aqueous, it is only a strong electrolyte if it's one of the 7 strong acids, or it's an ionic compound. Because it's aqueous does not automatically make it a strong electrolyte, because all those weak acids are aqueous and they're not strong electrolytes. Okay, so once I've recognized my strong electrolytes, we're going to dissociate them into their ions. We're going to break them apart into their ions. Everything else we're going to leave the same. So aluminum solid looks exactly the same. 6 HBr, I'm going to break that into 6 H pluses and 6 Br minuses. 2 aluminum bromides, I'm going to break that into 2 aluminums and 6 bromides. There's 3 bromines right there times 2. That's where the 6 came from. The hydrogen gas I left the same. This is called a total ionic, or just an ionic equation. So to make it into the net ionic form, we're going to cancel out spectator ions. Spectator ions look exactly the same on the left side of the arrow as they do on the right side of the arrow. I see 1 spectator ion here. I see 6 Br minus aqueous on both sides. So I'm going to cancel that out. And what's left is going to be my net ionic equation. What's nice about this for us? A couple of things. Number 1, the oxidation numbers are already visible for those 2. Number 2, there's only 2 elements. One of them is going to be oxidized, one of them is going to be reduced. The bromine was the one that we ignored. Now it's already gone. So it's easier to find oxidation numbers, and it is easier to identify oxidized and reduced. So I'm going to do one more. Nope, I lied. No more net ionic equations. So starting in part 2 of chapter 20 will be actually like the beginning of chapter 20. This was just review. Again, chapter 4 is your friend. Electrochemistry, it's dumb, but it's important, so we have to learn it. So, all right, next is part 2.